Excited to announce and present Eli Ben Sasson of StarkWare. They've obviously had a lot going on, and he's going to share a bit with you in the coming minutes.
Hello everyone. So the topic of my talk is going to be how StarkNet is going to reach 10,000 TPS. But also, I would like to address why would we want to reach 10,000 TPS in terms of demand and what will happen when we have that capacity, and also along the way. So first I want to discuss the how, and then we'll discuss the why. So a brief history of proving. Zero-knowledge technology started in 1985, and major points in the adoption of zero-knowledge technology have been Zcash. I was fortunate to be a co-founder of that. Today, most of the scaling going on layer 2s is done through Starks, which I co-invented in 2018, and StarkWare has been the first to productize through StarkX in 2020, and recently StarkNet. And by now, Starks are pretty widely adopted. Now, already in terms of capacity and demand, over the years that we've been scaling Ethereum using our first generation prover, which is called Stone, we've already seen pretty high peaks. For instance, we had the peak in user operation steps has reached 187. And the thing about StarkNet is that you can pack into one transaction many different user operations. So we already saw pretty high demand and, of course, capacity. And over the years with StarkX, we've saved over $1 billion in gas fees. By now, with the prices of Ethereum, it's more than $1.5 billion in gas fees and rising. So there was already pretty impressive scaling. Another thing you should know about StarkNet, it is, and this is the thing that causes me the most pride, is that it has the developer ecosystem that is fastest and most growing, and also the largest among all L2s. So if you're not yet part of StarkNet, you should consider joining. Now, let's go back to the question at hand, which is we want to scale StarkNet to reach 10,000 TPS, and when I say TPS, I'm going to talk about standard ERC20 transfers, and I want to, we're not there yet, so I want to discuss what are the bottlenecks and what are not the bottlenecks. Now, surprisingly, the proving is not the bottleneck. What do I mean by that? A few months ago, we did some stress testing on our proving stack, just to get ready for things like provisions, which happened last week and was the largest event of its kind, the largest airdrop of its kind, 1.3 million addresses, which went seamlessly with no glitches, and the whole system worked very well. So as we were testing the system towards it, we beefed it up to 1,000 to 2,000 TPS for several hours in terms of proving capacity, and the system can withstand that. Now, that's Stone. That's the current generation prover that has been in operation for roughly 4 years. So it's like the Boeing 747 that you use to haul a lot of weight and is battle tested. Stu, that we just announced yesterday, open sourced, and I'll share some details about that, it's probably going to be something like 100 times faster. So in terms of reaching ability to prove and process 10,000 TPS, we're very close to it. So this is not the bottleneck. Where is the bottleneck? And so again, I want to impress this on you. Proving is not the bottleneck. The bottleneck is elsewhere. It's in more conventional stuff. Where is it? So today we can operate at a range of between 90 and 200 TPS, depending for transfers, depending on how exactly the transfers are written in code. And probably by the end of the year, with the performance improvements that we're working on, we're going to reach something like between 200 and 500 on this side of the stack that includes the sequencer and everything that comes before the provers start working. So the bottleneck lies somewhere there before the proving commences. And I want to share with you some thoughts on how we can improve things there. before doing so, let me mention again that a little bit, brag about the next generation proving technology that we just, so the math breakthroughs behind it were unveiled a week ago in a beautiful paper called Circle Starks, that is joint work between Polygon and StarkWare. And the white paper has been out there for a full week. Yesterday, we released the open source of the first version of the prover. The notable things called STU. If you're looking and asking yourself why this geeky name, so STONE stands for Stark 1, and it's the first prover that we've been using, and STU stands for the second version. And of course, there's going to be Strez, Squat Row. I don't know about 5, like how we're going to 5. We'll figure that when we get there. So it's going to work over this very small field that can fit in a 32-bit register called the Mersenne 31 or M31 field. It's going to have a much more improved virtual machine. It's going to be operating with the Circle Stark, that I'll say a few words about it, and it's going to have a lot of other bells and whistles, such as the GKR lookup and mixed degree trace. There's going to be a lot more information about it tomorrow, shared. Towards the end of the talk, I'll give you a link. There are going to be a few talks about it, both by our engineering team sitting there. After the talk, you can come to Shachar and Andrew and ask them all about it. And Shachar is going to give a talk tomorrow, as well as Ulrich, one of the co-authors of the Circle Stark breakthrough. So consider attending it. Now, so the Mersenne M31 field is the field that is defined by the prime 2 to the 31 minus 1. So it's a Mersenne prime. And it has really great performance. It fits inside one register, every field element. It allows, these smaller field elements allow for better granularity for arithmetization. For those of you who are in the ZK research and building circuit technology. And you have pretty nice CPU and GPU operation because of the structure of the field. Come tomorrow and listen to Shachar's talk and you'll hear more about this. Where does Circle Stark come from? It turns out that to do Starks efficiently, you really want to be operating over a group, and hopefully a cyclic group that has size 2 to the k for pretty large k. Now the problem is that M31 doesn't have such a multiplicative group. So it happens. The degree to extension of it does have, but then you're going to move to 64 or 62-bit field words, and that's less efficient than 32-bit words. So to solve that, one solution could be to work over elliptic curve groups, and there's an abundance of sizes, so you can find one size that fits your needs. This was also work that was published by StarkWare a couple of years ago, but that's still pretty expensive. The better and new solution in this breakthrough uses a much simpler curve, the good old circle that we all know from, I guess from kindergarten, that goes like this. So all points that are at distance or whose, the sum of the squares of coordinate equals 1. So when you talk about regular Starks as the ones that are used in stone, the group that you're using is a set of numbers. You can think of them as lying on some line. Elliptic curves look a little bit like this. And here's another picture which I think you'll agree is much more pleasant. So that's the circle group. Some elements, so we are talking about modular arithmetic, so things are always taken, modulo the Mersenne prime. And so, for instance, the point 2 to the 15, 2 to the 15 happens to be a point on this circle. The magics of a finite field. Back to our bottlenecks. So this was a little detour, basically praising Stu, and I hope I got some of you intrigued that you'll want to hear more from Ulrich and from Shachar tomorrow, or just read the papers. But now I want to go back to the bottlenecks and unpack why is it that even though proving capacity can probably in 2 years reach something like 100,000 or more TPS, why is it that we have where are the bottlenecks and how can we go about trying to unclog them? So there are 5 different areas where things could get pretty crowded if you're talking about 10,000 transactions per second. The first place is the entry point, the peer-to-peer network and mempool. Then you have the full nodes that are basically tracking everything that is happening. You have data availability, what happens with all of the updates to the network coming from these 10,000 transactions per second. You have the block explorers that are supposed to save, the set of transactions over time. And then you have the sequencer, who is actually flooded with this, fire hose of transactions and needs to sequence them and process each one of them and update state accordingly. And remember, all of this comes before the proof. If the sequencer has ended and, given output this like nice big block with 10,000 transactions or even more, 100,000 if it's a 10-second time frame, the proving technology, well, not today, but certainly in 1 to 2 years, can easily gobble that up and produce proofs that would fit comfortably into Ethereum with very low gas cost. So all of the problem lies in these things. So let's unpack each one of these and see where we might see problems. So, and I'll jump to the end and say the sequencer is really the only one where you should anticipate some serious problems that can be resolved. So if you think about the mempool and the networking, it's not that bad, because if you do, it's roughly 4 addresses per one transaction to describe it, the recipient, the payer, a signature, the sum being sent. And at 10,000 TPS, that's 1.3 megabyte per second. It's not such a horrendous amount of information flowing around, right? Commonly, internet links are today in the hundreds of megabytes per second. So this is not going to be the bottleneck. Okay, so that thing's clear. What about the full node? So the full node is the thing that updates states and also verifies a proof. And the main thing to know about validity rollups is that full nodes have it sweet and easy. Why? Because you don't need to go through these transactions and check that they are valid. The proof does this for you. You only need to get the state diff, update your database after you verified the proof. But the proof is extremely succinct and very quick to verify. So the way a full node works, it receives a state update, it receives a Stark proof, it verifies the proof, and now it knows that everything is fine. So now state updates are much, much, much smaller than the number of transactions. Why? Because if you're operating at 10,000 transactions per second, I mean, let's suppose that a lot of people are buying their cups of coffee, so probably a lot of these things are going to the same addresses or coming from same addresses, and this means that the updates are going to be, these are not pairwise distinct pairs of addresses. They are pretty clogged together, and this is at least what we also see empirically in the trading systems, for instance, that we support today with StarkX. So folks like Paradex and DYDX and a bunch of the most scaled solutions today that are self-custodial are actually operating on the StarkX stack. So we see that that's not a problem. So this is not going to be an issue. Now, what about data availability? So if you go with full roll-up mode, well, this is going to be a problem. If you want everything on layer 1 of Ethereum or even inside blobs, that's probably going to be pretty blobous blob that you're going to need to use. So not sure that's what you want to do. But what you can do is you can use Volition with a lean and mean data availability solution, and you, of course, can use compression. Now, the nice thing is that, again, if you think about the data rates, they're not that big, and updating databases with the equivalent of something that is far less than, let's say 1 megabyte per second is something that is very commonly done and doable. So that's not going to be an issue either. I mean, assuming you have a data availability solution, but there's an abundance of them already existing. Okay. So what about block explorers? I mean, we're increasing with the complexity. So we said that 1.3 megabyte per second is what is communicated, but this turns out to be, if I got the math right, and I'm not very good at math, but you know, folks help me. So it's 120 gigabytes per day, which is a lot, and that turns out to be 43 terabytes per year. Now, what do you do with this stuff? Well, you know, if you today were to go to your bank and ask for data about transactions, probably you would get it back, you know, 6 months or a year, and beyond that, you would have to wait for a few days, right, for them to take it from some disk. So something similar. I mean, 43 terabytes is a large amount, but this is for, you know, block explorers. You can accumulate this for a few years, and then, of course, discard or put on some, you know, bigger disks. You can put older stuff. So again, this is, it's going to be costly, but block explorers, you know, hopefully they'll have good business doing this, and again, they can. So the sequencer is really the toughest problem, because the sequencer, as the name implies, turns out to be sequential. So there needs to be this processor that now processes one transaction after the other for 10,000 of them, you know, checking the signatures, going to the state and database, checking that there are enough funds, and so on and so forth. So the answer to this, and it's a, you know, magic wand that of course would need a lot of expanding, this is parallelization. But another thing that also could be done is, in terms of parallelization, you could also do things like post-processing and settlement, where you see, for instance, that each, I mean, you could have like many transactions that actually contradict each other, appearing where each one of them is individually valid. You now have double spends, but as long as that there's a fixed ordering on the transactions, and these are simple transfers, so you can sort things out. Okay, so now, another thing that gives us room for hope is that conventional systems, right, between, if you look at Visa, Alipay, WeChat Pay, these things, they today operate at TPS that is much higher than 10,000. At peak, they reach hundreds of thousands. Now, and one last thing is that this falls only on the sequencers. And in order to be a sequencer, you're already going to need to stake a lot of Stark tokens and be committed to it, so you'll probably be buying a pretty beefy machine. And again, in the context of validity rollups, because you have proofs, everyone else can verify your integrity without checking everything that you're doing, so you can actually get away with having larger operators operate in the network. Okay, so this is a tough problem, but you know, within hopefully 2 years, we can somehow solve it. So we talked about the how, but let's talk about why. Why would we want to reach 10,000 transactions per second and beyond? And we can get inspiration from the history of the internet. So until the late 1990s, there was very little usage of the internet. Why? So here's a quote from Wikipedia. I'll just read it out. The dramatic expansion of the capacity of the internet, thanks to all kinds of, you know, technology like fiber optics and other things like that, had a revolutionary impact on culture, commerce, and technology. This made possible the rise of near-instant communication by electronic mail, instant messaging, voice over IP, telephone calls, video chat, and the World Wide Web with its discussion forums, et cetera, et cetera. So what is the summary here? You had something that looked very promising, but until it had scale, you didn't actually see not even you know, an inkling of the kind of applications that will arise. So why am I saying this? Because StarkNet, I think the same thing will happen. And maybe 10,000 separate transactions would still take us a couple of years, maybe even 3 years. But if you're looking just at sheer compute on StarkNet, you can already do some pretty marvelous stuff that's going to be utilized this year already, and by a lot of the amazing applications building on us. So remember that we can support the largest transactions in terms of user operations contained one transaction had 682 user operations, and the peak UOPS that we had was near 200, and this already happened. So you're going to see a lot of layer 3s and complex logic, and wait, I want to talk about complex logic. So you're going to see things like on-chain gaming happening with a lot more logic, utilizing already the compute that is unleashed already today on StarkNet. So what I want to say is maybe for individual transactions, high rate, we're still 2 to 3 years away. But in terms of sheer computation power for single transactions that take a lot of computation steps, this will be a thing already this year. So Influence is basically, I think, either already launched or waiting for EAP 4844 to come out there and do its thing. On-chain game, probably going to be one of the most interesting ones. Do try it out. So summing everything up, how are you going to do it? We're going to do it through engineering, which is how we did everything we did so far. The sequencer is the main bottleneck, and probably the solution is something along parallelization. And why? It's not so much about TPS, but about compute. Compute is already pretty huge today, and I encourage all of you to try and utilize it. You want to hear more? Join us tomorrow for the StarkNet meetup. I'll leave you with this. Scan the QR code and join StarkNet. Thank you very much.